Hi. Dear students, I'm Dr. Arun Kumar, Associate Professor, Department of Mathematics, Sai with the Institute of Technology, Bangalore. So in this session, I'm going to discuss about how to check the convergence and divergence of a given infinite series using D'Alembert's ratio test. So in my previous session, we have discussed about Cauchy root test, how to check the convergence and divergence of that series using Cauchy root test. Now we'll use another one, D'Alembert's ratio test for convergence and divergence verification. So start with the condition of D'Alembert's ratio test. So it says if sigma un is a series of positive term, and if the limit n tends to infinity un plus 1, I mean n plus 1th term of your series divided by nth term un is equal to L, a finite number, then the series is convergent if L is less than 1. It is divergent if L is more than 1, and the test fails when L is equal to 1. So this is the statement or condition of the D'Alembert's ratio test. So just like the previous one, Cauchy root test, only this condition is different. So there we have limit n tends to infinity, un power 1 by n, but here it is limit n tends to infinity, un plus 1 by un, I mean n plus 1th term of a given series by nth term of a given series. If the ratio is a finite quantity and based on the value of that, I can discuss about convergence and divergence. If the value is less than 1, it is convergent, more than 1 is divergent, and if L is 1, again, even this ratio test also fails. We have to go for other tests for verification of convergence and divergence. And here the most important thing is we can try to apply this test when the series contains some factorial terms in the expression. And if the series is in this form, I mean carry over series like 1 by 1, 1 into 2 by 2 into 3, it is carry over 1, 2, 3 by 2, 3, 4 like this. We can identify those problems. Means I can apply D'Alembert's ratio test to solve. So you can apply for other cases also, but if these cases are there, means factorial notation carry over means 100% I can apply D'Alembert ratio test easily. For other cases also, I can try to apply D'Alembert's ratio test. So now let us see how we can calculate this limit and how to check the convergence of a given infinite series using D'Alembert's ratio test through certain examples. Let's start with the first problem. Test the convergence of the series 1 square by 2 plus 2 square by 2 square, 3 square by 2 cube plus 4 square by 2 power 4. See, even this is not contains factorial, not even a carry over series. But however, I can do this by using ratio test. That's why I said, if the problem contains factorial or carry over, I can directly apply D'Alembert's ratio test. So easily I can guess. For other series also, I can apply this ratio test. Depends on what is our un and un plus 1. So this ratio, when you calculate, so if you get a simple term and can able to calculate the limit of that, means you can apply this D'Alembert's ratio test. So easily. So it can applicable, this test is applicable for most of the infinite series. So anyway, let us see how we can test the convergence of this infinite series. So let sigma un equals, it is 1 square by 2 plus 2 square by 2 square plus 3 square by 2 cube plus 4 square by 2 power 4 and so on. So I'll write the nth term of the series, sigma un equals, it is sigma, yeah. Now see, if you look at the numerator of this infinite series, it is 1, 2, 3, 4, 5 like this. The nth term will be n. And here 1 square, 2 square, 3 square, 4 square, 5 square. If you continue like this, the nth term will be n square. Divided by denominator, start with 2, 2, 2. And here the power is 2 power 1, 2 power 2, 2 cube, 2 power 4 like this. So it becomes the nth term is 2 power n. 2 power n. So the summation series can be written like this. Summation n square by 2 power n. So on comparison, I can write this as un is equal to n square divided by 2 power n. This is the nth term of this. Now, you can apply D'Alembert's. To apply D'Alembert's, UN is ready. So we have to find UN plus 1. So here UN plus 1 becomes, so replace n by n plus 1. So get n plus 1 whole square divided by 2 power n plus 1. So this is our UN plus 1. Now let us take the limiting condition of D'Alembert's ratio test. That is limit n tends to infinity UN plus 1 by UN. So this is equal to limit n tends to infinity. So UN plus 1 is this n plus 1 whole square divided by 2 power n plus 1. This whole thing divided by this n square by 2 power n. So and we can write this as limit n tends to infinity. So I'll write this numerator as n plus 1 whole square by n plus 1 whole square by. So I can write this 2 power n plus 1 as 2 power n into 2 power 1. See this one, 2 power n plus 1 is 2 power n into 2 power 1. And this, this will go to the numerator. And I can write this as into 2 power n by n square. So this divided by means I can write this as 2 power n by n square. So now this 2 power n gets cancelled. And I can rewrite this as, see, you can observe here, this 2 is a constant. I can take it outside. It is 1 by 2 limit n tends to infinity. It is n plus 1 whole square divided by n square. So this is the simplified term. Now if we substitute a limit of this n tends to infinity and simplify, we get the value of limit, and I can decide about the convergence or divergence. But here the problem is, if I substitute the value of n straight away, it becomes infinity plus 1, that is infinity. Here also get infinity square. So it becomes infinity by infinity, indeterminate. So I cannot put the limit directly. So I simplify like this, 1 by 2. Limit n tends to infinity. See, the denominator I'll write as it is, n square. Whereas in the numerator, let us take n outside. If I take n outside here, so square is there. So it becomes n square. So since we have taken n outside, so it becomes 1 plus 1 by n. 1 plus 1 by n whole square like this. I'm just taking n outside so that it becomes 1 plus 1 by n. So if we split it, we get n square into 1 plus 1 by n whole square. So that this n square gets cancelled. So this implies L equals, it is 1 by 2 into, put the value of n in this. N is infinity. So if I substitute here, it is 1 plus 1 by infinity whole square. So this implies L is equal to, 1 by infinity was 0. So 1 plus 0 is 1. 1 square is 1. So 1 into this half. It gives half, and this is less than 1, less than 1.5. So according to the condition of D'Alembert's ratio test, so I can conclude that this series is convergent. So therefore, you can say the series is convergent. So this is how we can examine the nature of a given infinite series using D'Alembert's ratio test. So it is a simple test here. The only thing is you have to write the nth term, take that as un, write its n plus 1th term. Just put n is equal to n plus 1 in your un, you get un plus 1. So find out the ratio un plus 1 by un and calculate its limit as n tends to infinity. And based on the value of that, we can decide whether the series is convergent or divergent. So let us apply this test for some more examples. I'll take one more problem now. Discuss the nature of the series. Discuss the nature of the series. X plus x square by 2 factorial plus x power 4 by 3 factorial 2 factorial plus 1. So this is the problem here. So, and if you observe this example, This is the series which is having factorial terms, 2 factorial, 3 factorial and all. So as per our note, if the series contains factorial terms, so it is a 100% problem related to D'Alembert's ratio test. So let us apply D'Alembert's ratio test and we will see how to solve this problem, how to check the convergence or divergence nature of this. Just go to the next page. So here let sigma un equals the given series as it is x plus x square by 2 factorial plus x power 4 by 3 factorial plus so on. So or I can write this as sigma un equals it is sigma. So what is the nth term of this? So here x square, x power 4, next will be x power 6. So like this. So it becomes x power. So 2, 4, 6 and all means it is an even number. I can write it as 2n. So if n is 1, it is 2. N is 2, it becomes 4. N is 3, it becomes 6. N is 0, n is 1 means it becomes x power 1. Leave the first term and calculate this. Leave the first term and you can calculate this. So next is 2 factorial, 3 factorial, 4 factorial. It becomes n plus 1 factorial I can write. Right. So I can leave the first term to count because there is no continuity here. So since it is an infinite series, the same thing I did in Cauchy root test. So leave the first term and find out the nth term of this. X square, x power 4, x power 6 and all can be written as x power 2n. 2 factorial, 3 factorial, etc. can be written as 2, 3, 4 means n plus 1 factorial. So I can start from n is equal to 1 here, 1 to infinity. Can leave the first term because of infinite series. If n is 1, this term will come. If n is 2, this term. N is 3 means the next term. So this will continue. So on comparison, I can write un equals, it is x power 2n divided by n plus 1 factorial. Now, so this is the nth term means the n plus 1th term is here un plus 1 is nothing but replace n by n plus 1. It becomes x power 2n plus 2. If I put n is equal to n plus 1, it becomes 2 into n plus 1. That is 2n plus 2 by denominator. If I put n is equal to n plus 1, so it is n plus 1 plus 1. It becomes n plus 2 factorial. Now consider the limit. Consider limit n tends to infinity, un plus 1 divided by un. So this is equal to limit n tends to infinity. You know, un plus 1 was, it is x power 2n plus 2 divided by n plus 2 factorial into, so this divided by, I make it as into. So when I made it as into, you know, this becomes reverse. N plus 1 factorial divided by x power 2n I can write. Because divided by this means it is 1 by a by b, can be written as b by a. Now simplify this. This is equal to limit n tends to infinity. So, you know, I can write this x power 2n plus 2 as, it is x power 2n into x square divided by, you know, n plus 2 factorial can be written as n plus 2 into n plus 1 factorial. So means, you know, it is something like, suppose you have 10 factorial. You know, 10 factorial can be written as 10 into 9 factorial. In the same way, n plus 2 can be written as n plus 2 into its previous term, n plus 1 factorial. 10 factorial is 10, its previous term, 9. 10 into 9 factorial. N plus 2 is n plus 2, n plus 1 factorial into, this is n plus 1 factorial by x power 2n. So that this x power 2n term, n plus 1 factorial, n plus 1 factorial gets cancelled. So here I can write this as L equals, so this x square is free from n. So it is x square into limit n tends to infinity. It is 1 by n plus 2. If I substitute a limit for this, it is x square into 1 by infinity plus 2. If I put n is equal to infinity, and infinity plus 2 is infinity, and 1 by infinity was 0, this is 0. So this implies L equals x square. So this shows that the convergence of this series depends on the value of x square. So I can conclude like this. So this series is convergent if x square less than 1, comma divergent if x square greater than 1, and the test fails if x square is equal to 1. So this is the nature of this infinite series. This is how we can verify the convergence or divergence nature of an infinite series using D'Alembert's ratio test. So, and you can observe that the second problem is with respect to factorial terms. So as I told, if there is a problem containing factorials, we can straight away solve that by using D'Alembert's ratio test. So in the same way, we can solve some more problems. I'll just go to the next problem. The third problem is test the convergence of the series x by 1 into 3 into 5 plus 2x square by 3 into 5 into 7, 3x square by 5 into 7 into 9. So it is something like it is 1, 3, 5 carry over is there. Okay, so the terms also increasing means also it is called as carry over. So this problem, let us see how to solve by using the D'Alembert's ratio test. So let sigma un. So here straight away I'll write the nth term of the series summation. I'll write. So this is x. See here you can see 1 into x, 2x square, 3x cube, next 4, something like this. So it becomes n. X square, x cube means it becomes x power n divided by denominator. So denominator is most important here. See, if you look at this 1 into 3 into 5, I'll take only the first factors of the denominator. 1, 3, 5, next will be 7 like that. So 1, 3, 5 means I'll write here 1, 3, 5, etc. means. So A is 1 and D is 2. So A plus n minus 1 into D means it is 1 plus n minus 1 into 2. So it becomes 2n minus 1. So the first term was 2n minus 1. Right. So 1, 3, 5, etc. A is 1 and common difference is 2. So 1 plus n minus 1 into D. So it is 2n minus 2. Minus 2 plus 1 is minus 1. In the same way, if I take 3, 5, 7. So if I take 3, 5, 7, what will come? Just you have to identify. 3, 5, 7, etc. means it is 3 plus n minus 1 into D is again 2. So it becomes 2n minus 2 plus 3, it is plus 1. So it is 2n plus 1. And the next term is 3, 5, 7, 9. Means it is 5 plus n minus 1 into 2. So it is 2n plus 3. 2n plus 3. So just one factors you take. 1, 3, 5, write the nth term. 3, 5, 7, write the nth term. 5, 7, 9, write the nth term. So that the nth term of the series, un is nothing but it is n into x power n divided by, it is 2n minus 1 into 2n plus 1 into 2n plus 3. So if this is the nth term, so then n plus 1th term becomes, so replace n by n plus 1. So it is n plus 1 into x power n plus 1 divided by denominator. If I put n is equal to n plus 1 here, so it becomes 2n plus 2 minus 1. It becomes 2n plus 1 into, if I put n is equal to n plus 1 here, it is 2n plus 2 plus 1, 3. 2n plus 3. And this is 2n plus 2 plus 3, 5. So this is n plus 1. So I got un and un plus 1. Now we compute the ratio of this. Just go to the next page. Now consider consider limit n tends to infinity, un plus 1 divided by un. So this is equal to limit n tends to infinity. I'll write un plus 1 first. So un plus 1 was, it is n plus 1 into x power n plus 1 divided by denominator is, it is 2n plus 1 into 2n plus 3 into 2n plus 5. So into, so this 1 by un. So un is this, 1 by un means it is a reciprocal of this. So reciprocal of this means this will go to the numerator and this term will come to the denominator. So I'll write this as the numerator becomes, it is 2n minus 1, 2n plus 1, then 2n plus 3. The denominator was nx power n. So this is 1 by un, reciprocal of un. Now if you observe here, this 2n plus 1, 2n plus 1, 2n plus 3, 2n plus 3 gets cancelled. And further I can write this as limit n tends to infinity. It is n plus 1. See, this x power n plus 1 can be splitted as x power n into x divided by denominator was, it is 2n plus 5 here. Into here it is 2n minus 1 divided by n x power n. So that again this x power n gets cancelled. So I get L equals, I can take x outside now, this term, x outside. So it is limit n tends to infinity. So here it is n plus 1 into this term. It is n plus 1 into 2n minus 1. Divided by this is n into 2n plus 5. So also I cannot substitute a limit directly because if I substitute a limit directly, it becomes indeterminate. So again, I'll take n common from this term in numerator and denominator n common from this. I can write this as n into, if I take n outside here, this, it is n outside means it is 1 plus 1 by n. 1 plus 1 by n. In the next term, if I take n outside, n into it is 2 minus 1 by n divided by denominator n into, if I take n outside in this, it is n into 2 plus 5 by n. So that this n in the numerators gets cancelled. And now I can substitute a limit. This is equal to x into, substitute a limit. It becomes 1 plus 1 by infinity into 2 minus 1 by infinity. Divided by denominator, it is 2 plus 5 by infinity. And this implies x into, see, 1 by infinity is 0, 1 plus 0, this is 1. Into, this is 1 by infinity is 0, 2 minus 0 is just 2. Divided by denominator, 2 plus 5 by infinity is 0, 2 plus 0, again it is 2. So again this 2 gets cancelled. So we get L is equal to x. So for this problem, again we got answer in terms of x, and we can conclude that this series will be convergent if L is x is less than 1, it is divergent if x is more than 1, and this test fails if x is equal to 1 in this. So I'll just write like that. This series is convergent if x less than 1, comma, divergent if x greater than 1, and the test fails if x is equal to 1. So this is a way of verifying the convergence of the given infinite series using D'Alembert. So this is a common procedure for all problem here. So I'll take one more problem of D'Alembert's, the fourth one. Test the nature of the series sigma n is equal to 1 to infinity 4 into 7 into etc. 3n plus 1 divided by 1, 2, etc. up to n into x power n. So this is the problem given. So let us see how to verify the nature of this, whether it is convergent or divergent for this. So in this problem, straight away they have given a nth term. So I'll write the nth term of the series. So here un is nothing but it is 4, 7, etc. up to 3n plus 1 divided by 1, 2, etc. up to n into x power n. So now I want to write n plus 1th term. N plus 1th term. See, the n plus 1th term of this will be written like this is nth term. N plus 1th term means this term and its next term. So I will write like this. It is 4, 7, etc. up to 3n plus 1 into its next term was, it is 3n plus 3 plus 1, 4. 3n plus 4. I mean, I'm replacing n by n plus 1 here. So it is 3a into n plus 1 plus 1. 3n plus 3 plus 1, it is 3n plus 4. So till here it is nth. So I've written the term as it is because for cancellation purpose, I require this one. So n plus 1th term means what? N terms plus next term I have to write. Nth term is this n plus 1 divided by denominator. Again, it is same. 1 into 2, etc. up to n, and its next term is n plus 1. This is the term up to n plus 1 into x power n plus 1. Can write like this. Here, this is numbers are continuing here. This is a carryover series. This is a carryover series. When it comes to a carryover series, we have to retain this term as it is. In the carryover series, the nth term will include this one also. N plus 1th term will include this term also and its next term also. We have to write. But this x power n is, it is a variable. So I can write directly x power n plus 1 here. So now take a ratio. Consider limit n tends to infinity un plus 1 by un. This is equal to limit n tends to infinity. I'll write un plus 1 first. 4, 7, etc. up to 3n plus 1 into 3n plus 4 into this x power. See here itself, I'll simplify. This x power n plus 1, it can be written as x power n into x divided by denominator. It is 1 into 2, etc. up to n into n plus 1. This whole thing divided by un. Un was, it is 4, 7, etc. up to 3n plus 1 divided by 1, 2, etc. up to n into x power n. So un plus 1 is this divided by un. Now you can cancel the terms. This x power n gets cancelled. And the terms up to this 3n plus 1 gets cancelled in the numerator. And terms up to n gets cancelled in the denominator. Since it is a carryover series case, as I told you, to retain this entire thing so that I can cancel and rewrite the series. So this n terms gets cancelled. Only n plus 1 term will remain in this carryover. Right. So in the carryover, only n plus 1 term will remain. N terms gets cancelled because of this retention. And now this x is free from n. I can take it outside. So it becomes x into limit n tends to infinity. Now what is remaining here? It is 3n plus 4. 3n plus 4 divided by denominator is just n plus 1. 3n plus 4 here divided by n plus 1. All this term gets cancelled. So in carryover series, entire nth term gets cancelled. Only this n plus 1th term at the end, whatever you will write, that will remain. Now again here, I cannot substitute a limit because it becomes indeterminate, n by n. So I can take n common and simplify. So this is x into limit n tends to infinity. If I take n outside, it is n into 3 plus 4 by n. Divided by denominator, if I take n outside, it is 1 plus 1 by n. So that this n gets cancelled. And now if I substitute a limit for this, n here, it becomes L equals, therefore L equals, it is x into, I will substitute a limit straight away. It becomes 3 plus 4 by infinity. 3 plus 4 by infinity divided by denominator 1 plus 1 by infinity. 1 plus 1 by infinity. 4 by infinity is 0 and even 1 by infinity is 0. So you get 3 plus 0. This is equal to x into this is 3 plus 0 by 1 plus 0. So this gives L is equal to 3x. L is equal to 3x. So now the value of this L depends on this x, 3x. So the series is convergent when 3x is less than 1, divergent if 3x is more than 1. So I can conclude like this. So this series is convergent if 3x less than 1. So this is same as x less than 1 by 3. 3x less than 1 can also be written as x less than 1 by 3. Take this 3 to the right hand side. Comma, divergent if 3x greater than 1, or I can say x is greater than 1 by 3, and test fails when 3x is equal to 1 or x is equal to 1 by 3. So it depends on the value of 1 by 3. Okay, so if x is less than 1 by 3, it is convergent. If x is more than 1 by 3, the series is divergent. And if x is equal to 1 by 3, then I can conclude that the series is fails here. The test fails. So this is how we can verify the convergence or divergence nature of the infinite series using the D'Alembert's ratio test. So I can apply this test to solve other problems also. I'll just give few problems, 1 or 2 problems for practice purpose, only 2 problems. So you can try these problems by applying D'Alembert's ratio test. I'll just write the 5th one. Examine the nature of the series. Nature of the series. We can take this carry over series, one of the easiest one. 2 by 3 plus 2 into 3 by 3 into 5 plus 2 into 3 into 4 divided by 3 into 5 into 7 and so on. So this is the carry over series problem, guys. This one. So while writing nth term, you have to include, you write the nth term as 2, 3, 4, 5, 6 like that up to nth term, and n plus 1th term, you have to retain that nth and you have to write its next term. Just like previous problem, you have to write the nth term and n plus 1th term of this. Next is test the convergence of the series. Test the convergence of the series. You can take this 1 by 2 root 1 plus x square by 3 root 2 plus x cube by 4 root 3 plus 1, where x is greater than 0. So you can try these 2 problems by applying D'Alembert's ratio test. You can examine the nature, whether the series are convergent or divergent, just like the previous 3-4 problems. So this is about your testing the convergence or divergence nature of infinite series using D'Alembert's ratio test.